Alright, today we're going to start looking at power functions. We're going to look at end behavior, whether a function is odd or even. There's a lot of stuff that we're going to talk about with functions today. So first, let's look at this on page 226. Power function. Power function is a function p of x equals a times x to the n, where n is a non-negative integer. N is a power. See, these are power functions. What power is that one to? Yeah, the first power. Power 1. Exactly. Okay, so let's look what's happening. 1 is a straight line, right? This squared, cubed, 4th, 5th, 6th. What's happening there? Alright, let's do some exercises here. Loosen up. Loosen up. You don't want to hit anyone. Alright. Y equals x. What does that look like? Like that, right? Y equals x squared. What does that look like? Alright. Y equals x cubed. What does that look like? Yeah. X to the 4th. What does that look like? X to the 5th. X to the 6th. See a pattern there? What's x to the 7th? What's x to the 8th? Okay, great. Alright, sketch and label. Aren't you so glad none of that's on video? Like, it's just going to be this, and people are going to be like, I wonder what they're doing. Yeah. Alright, sketch and label the next two graphs. So what do you think the next two graphs will look like? It's going to be y equals x to the 7th, y equals x to the 8th. That's what you're looking at right there, those two. So what do you think x to the 7th is going to look like? Yep, it's going to be like this. And x to the 8th? Yep. Touchdown. Oh, it is a touchdown. Okay. Good. Alright, look over on page 227 at question B. I'm going to leave these pictures up here so you can kind of look at them. So, you look in your book, but I'm going to look up here. State any observances or patterns that you notice about the graphs of the sequence, or graphs in the sequence. What do you notice about these graphs? They get wider. Okay, they get wider as the power increases. They seem to get wider. Okay, the more flat that it is, maybe. They get wider here at the origin. What else do you notice? Or do you need time to write that down? What do you notice about odd degrees? Okay, yeah, they're this. They point up and down, right? Odd degrees point up and down. What about even degrees? Right. The even degree functions point up only. Alright, I want you to do C and D by yourself, and then we'll talk. Okay, for C, a general statement about the graph of a power function raised to an odd degree. What does that look like? Other than they point up and down. Can you be more specific? Where does it start? We're reading it left to right. Where does it start? It starts down and it moves up to the right. Okay, so it starts down below the origin. And what happens at the origin? The higher the degree, it sort of flattens out, right? And then it moves up to the right. What about a power function raised to an even degree? Okay. It's concave up. And what happens at the origin? Flattens, yeah. The higher that power is, the wider, the more flat it becomes. Okay, let's talk about end behavior. This is on page 228. End behavior. End behavior is exactly what it sounds like. It's what the function is doing on the end. Okay, here and here. Those are the ends. So we're talking about end behavior. Now, some people get these kind of confused. You can write end behavior using this notation. And what this is saying is it's saying as x approaches infinity this way. That's x approaching infinity. Okay, it's going off to infinity. So as x approaches infinity, f of x is also approaching infinity. It's going on up forever. Right? F of x is the graph. X is what you're putting into the problem. F of x is the y that's coming out. As x approaches negative infinity, that's this one, f of x is also approaching negative infinity. Okay, it's going down forever. So that's end behavior. What is the graph doing on the end? I want to talk about the end behavior of these, and then we'll do what they're actually asking us to do. But I just want us to talk about end behavior first. What's happening here? What's happening with the ends of the graph? It's a straight line. So what's happening on the end? Right here, as x is getting closer to infinity, what's happening to f of x? It's also getting closer to infinity. What's happening this way as x is approaching negative infinity?
Is that like a 2 with 0 together?
Infinity? Yeah, it's like a sort of like a sideways 8 or something. Yeah. Alright, so what's happening to f of x here? It's also going to negative infinity. Okay? Over here, what about this one? As x approaches infinity, what's happening to f of x? If I go that way, what happens to f of x? It's also approaching infinity, right? On the other side, this way, as x approaches negative infinity, what's happening to f of x? Right, it's approaching infinity. Not negative infinity, because negative infinity would go to the yard. Down. It's also okay, great. Alright, negative f of x. This one right here. If this one's negative, what's that going to look like? It's going the other way, okay? Like this? Alright, so what's my end behavior now? As x approaches infinity, what's f of x doing? Approaching negative infinity. As x is approaching negative infinity, what's f of x doing? Yes. Okay. Alright. If I put a negative here, that's going to be a negative x squared. What does that look like? Like that. So in behavior, as x is approaching infinity, what's f of x doing? And as x is approaching negative infinity, what's f of x doing? Approaching negative infinity also. Yes. Hey, how about this one? It's going to be a negative x cubed. It's going to flip it. Start I. So as x approaches infinity, what's f of x doing? Okay. As x is approaching negative infinity, what's f of x doing? Alright, fill in the chart on question B on page 229. Fill in that chart. Question B on 229. Alright, odd degree power functions when a is greater than 0. What happens on odd degree power functions when a is greater than 0? As x is approaching infinity, what does f of x do? It approaches infinity. And as x approaches negative infinity, what does f of x do? Yes. What does that look like? Looks like a down up. degree power functions when a is greater than 0. As x approaches infinity, what does f of x do? Approaches infinity. As x approaches negative infinity, what does f of x do? What does that look like? U. What about odd functions when a is less than 0? As x is approaching infinity, what is f of x doing? And as x is approaching negative infinity, f of x is approaching, yes, what does that look like? Right, it starts high and it ends low. Alright, even degree power functions when a is less than 0. As x approaches infinity, f of x approaches what? Yep. And as x approaches negative infinity, f of x approaches, yep, what does that look like? Even degree functions, the end behavior matches. It's up, or it's down, okay? On an even degree function, the end behavior is going to match. On an odd degree function, the end behavior is opposite. It's up, down, or down, up. Okay? So they don't match. They're opposite. So everybody have that chart filled in? Alright, let's talk about symmetry on page 234. Okay, if a graph is symmetric about a line, then the line divides the graph into two identical parts. Special attention is given to the line of symmetry when it is the y-axis. Okay, so Olivia says that the graph has no line of symmetry because if she reflected it across the y-axis or the x-axis, it would just change the graph to look like an odd degree power function with a negative value, thus not looking like a mirror image. Randall says that the graph has no line of symmetry because if he looks at the x value at 1 and negative 1, the y value is not the same, so there can't be symmetry about the y-axis. Also, if he looks at the y value at 8 and negative 8, the x value is not the same, so there can't be symmetry about the x-axis. Shedrick said that there is some type of symmetry. He noticed that if he looks at the point 2, 8 and the point negative 2, 8, or the point negative 2, 8 is also on the graph. Likewise, he looks at the point 1, 1 and notices that negative 1, negative 1 is also on the graph. He concluded that it must have reflection across the x and y-axis at the same time. Who is correct? Explain your reasoning. What do you think is right? Shedrick. Yeah, even if you don't use math, you just use your reasoning from all these questions I've asked you in the past. Shedrick is correct. There's symmetry because for every point x, y, the point negative x, negative y is on there, okay? So for 3, 3, there's a negative 3, negative 3. For, oh, that's 1.5. 1.53, negative 1.53. For 2, 8, there's a negative 2, negative 8. So whatever point you have over here, you have that same point negative over here. So he is correct. Okay? graph of an odd degree basic power function is symmetric about a point. Function is symmetric about a point if each point on the graph has a point the same distance from the central point, but in the opposite direction. Special attention is given when the central point is the origin, as it determines that the function is odd. Okay? That's what you're looking at right there. If you replace both x, y with negative x, negative y, the function remains the same. We've got 3 examples. And then if you look just a little bit further down, very important right here, an even function has a graph symmetric about the y-axis. An odd function has a graph symmetric about the origin. Now, does it have to be symmetric about the y-axis or symmetric about the origin? No, you can have an even, an odd, or neither. It can be even, it can be odd, or it can be neither.